this is the last tutorial we have for the day. It's going to be given by Dr. Brian Broll. He is a researcher at the research scientist at the Software Integrated System in Vanderbilt Universities. So today his tutorial going to be hands-on introduction to deep learning with DeepForge.
Okay, so today we're going to be, thank you for joining me in the tutorial, a hands-free introduction to deep learning with DeepForge. As I mentioned in my introduction, I'm Brian Broll, and I'm a research scientist at Vanderbilt University, specifically at the Institute for Software Integrated Systems. So here's a little overview of the plan for the tutorial so far. We're going to start with a few slides just on like what DeepForge is, some of the core concepts and such, so that it's hopefully smoother once we actually jump into the environment itself. And then we're going to jump into a tutorial working with the CFAR10 dataset, and following that, we're going to get into time permitting some more like advanced topics and some demos of some of these more advanced capabilities. And then we're going to finish up with a little bit of Q&A, but of course, as I mentioned at the beginning, questions are certainly welcome at any time. Okay, so a little bit of necessary background. So although we're going to be jumping into deep learning, this is a little bit more of a practical or, again, hands-on sort of tutorial. So I'm not going to spend a lot of time with proofs or things like that, and I suspect people have at least heard of deep learning in the past. If there are more questions on some of this background, I guess we can cover some of it as it arises, but I wasn't planning on getting into a lot of necessarily depth on some of more like the theoretical foundations and such. That said, a deep neural network is an artificial neural network with multiple hidden layers, and the deep learning is generally a pretty flexible technique, and it's been applied to a number of problems in a variety of different domains. So things like automatic speech recognition, image segmentation, image classification, and such. And I know there have also been applications of this in various scientific domains, including things like redshift estimation, which we do have a little bit of a demo for at the end, time permitting. And of course, it's been applied to reinforcement learning and imitation learning and all sorts of different problems. And oftentimes, I think largely due to their expressiveness, if they're able to be applied, they're generally pretty good at achieving the state of the art. If you're just looking at, again, trying to achieve the highest score in some of the sort of objective function in some domain, they generally score very highly in those types of regards. All right, so now jumping into DeepForge itself. So DeepForge is a platform for applying deep learning within diverse scientific domains. And DeepForge itself is designed to integrate within the existing infrastructure. So the idea is to really try to help make deep learning more simple or accessible for people to use in these other domains, while promoting collaboration and workflow reproducibility. So being able to recover the code that you that produced whatever the given artifact is. I clarify the workflow reproducibility because you can also get into questions about random number generation and areas of stochasticity in various training algorithms, which isn't necessarily the goal. Anyway, the approach that DeepForge has taken in trying to achieve these design goals has been through domain-specific visual and textual editors. So there's, as we'll see later, there's a visual editor for designing neural networks that gives you feedback about any errors and shape, and as well as shape information. So shape of the tensors, that is, flowing between the layers. And this is all given to you at design time rather than having to wait till runtime. And then, of course, we also want to make it easy to create and execute workflows from within the browser. And again, using your existing infrastructure, because we're not trying to, because a lot of these scientific domains already have certainly other computationally intensive tasks, and as a result, their own high performance computing resources. So we don't want to try to convince people to, it's a lot, we don't want to try to move people to a different compute infrastructure, compute infrastructure when they certainly already have their own. Anyway, there are also other additional things like automatic version control to try to make it easier to promote reproducibility for the users, as well as things like data provenance, which we'll get into detail a little bit more later, but it is closely related to automatic version control, but kind of exists outside of this concept of branching and merging and such. There are also, we also support things like real-time collaborative editing, as well as, again, as I've mentioned already, this integration with existing high-performance computing and storage resources like SciServer and S3. So from a real high level, we, when you're working within DeepForge, you can design like neural network architectures given these visual editors. So these aren't just a like a diagram of the architecture that's generated from some code, but this is like an interactive editor that you can actually create and debug and design your architectures within. And then after you've designed an architecture, this can be referenced within like a workflow shown here in the center. This is a workflow or a pipeline, which is a more commonly used terminology in DeepForge. This is a pipeline consisting of 5 different operations. So first, it's in this case, we're running a cast jobs query, which might be familiar if you've used SciServer or familiar with SciServer. If you're not, it's don't worry about it. And then we, after querying metadata about various for various spectral data, then the second operation is going to basically download some of the image content associated with the metadata, then do a pre-processing step, a train and validate step, and then visualizing the predictions. And then once we've designed a pipeline, then this pipeline can be actually executed from within the browser, where you get feedback as shown here on the right. So in this case, we have job nodes that correspond to each operation. And as we can see, it's isomorphic with the pipeline itself. The first 3 of which of these jobs are green, which signifies that they've completed successfully. The yellow one is currently executing, and then the gray one has yet to execute. So now to some of these core concepts. I've already mentioned them sort of in passing, but to be a bit more explicit. DeepForge consists of really 2 different categories of concepts. There are the concepts for creating these executable pipelines, as well as some concepts for designing the neural network architectures. Now, these concepts should be somewhat intuitive because we're again trying to maintain accessibility and make it a pretty, hopefully, easy onboarding process. So the 4 main concepts for creating executable pipelines are operations, pipelines, jobs, and executions. And we saw these in the previous slide, where there was a pipeline composed of operations, which when we run, takes a snapshot of it, which becomes an execution, which is much like an instance. Like it's a snapshot of it that is composed of jobs. Now these jobs correspond to each operation, but they have additional runtime information like plots that were produced when they were executed, or standard out logs and things like that. There are really just 2 high-level concepts for designing neural network architectures within DeepForge, or at least maybe the 2 most coarse-grained concepts that we need to understand to be able to use DeepForge are really just architectures and layers, which if you have prior experience with neural networks, these shouldn't be any big surprise. Now, digging into these pipeline concepts a little bit further, operations are functions like those gray boxes that we saw 2 slides ago. And they have multiple named inputs and outputs. They have attributes and references can also be defined for an operation. So for example, like that train validate step might have like iterations or epochs as an attribute that's set when you're designing the pipeline. So it's known, prior to execution. Pipelines represent some, in our case, machine learning tasks composed of operations, though as you can probably tell from these definitions, it's not necessarily constrained to just machine learning tasks, but that's the overarching goal in this context. But certainly this is a bit more generic of a concept. So, but as an example of some pipelines that you might have, it could be like a training pipeline or a prediction pipeline, or you could be doing data augmentation or pre-processing or things like that. Or again, as shown in the earlier example, you could have a pipeline that does all of these things. It fetches the data, pre-processes, then trains and validates, and then like visualizes the predictions and tries to help the user gain intuition about what has been learned. Now, pipelines can also contain input and output operations, where basically you can load your own custom data in or save whatever the output is automatically back to DeepForge. All right. I know we're kind of, if there are, still in the earlier phases of this, but if there are any questions, again, feel free to jump on in. And I'm going to try to go through this somewhat quickly, but I wanted to, lay the groundwork. So hopefully the transition into the tool itself is straightforward. So one example pipeline here is this one, where at the top we have this an operation that downloads the MNIST data set. It returns the training data to the train operation and a testing data, which is the testing data is passed to the scoring function or operation. Now this train operation has a few attributes: the batch size, epochs, and the model to use, which is a pretty simple one here, which is a simple one here named just MLP for multi-layer perceptron. And then the train model is produced as an output and also passed to this score model operation, which scores it using the testing data. Again, we'll see more of this in a moment, but all right, the two remaining concepts are jobs and executions. Now, the jobs are basically taking basically an operation that's that includes a little bit additional information about the like the execution state and any produced outputs like plots and such. And then an execution again is isomorphic to the original pipeline, but it can actually be executed, or it can actually run and contain some of this additional information. Now, the neural network concepts themselves, as I mentioned before, are pretty standard. So basically, we have these neural network architectures, and they're composed of layers. Layers are parameterized in a number of different ways that of course depends on the layer. So like dense layers you can configure the number of units, or you can convolutional layers can have things like kernel size, and dropout layers can have a dropout ratio, etc. As one more quick example before we start jumping into the demo itself, here the visual editor, these two concepts that we've referred to can be seen as visual editor. So that we're looking at a section of an architecture. So we have a convolutional 2D layer connected to a max 2D layer connected to a dropout layer. And we'll see some of these features more in a moment. But if you start seeing like a red highlight, as you might guess, that means that there's an error. And hovering on connections will show you the shape of the data flowing through. Now, one comment before we jump into things, you might see none a lot as the first dimension. And that's because you don't always need to provide the batch size when you're finding these architectures. So like, so none is usually the batch size, and if it's set to none, that's fine, certainly. All right. Without further ado, I'm going to jump over into the hands-on portion of this. So I have this GitHub repository where we can get our starter project, and as well as the slides here. Now, one other quick comment. or question, I guess, for the moderator is I do have some user accounts that the attendees will need to use to log into DeepForge, and I'm not sure of the best way to distribute those. I had initially been imagining one-to-one conversations via chat, like just sending them privately, but now that we don't have chat, that plan has kind of gone out the window.
I mean, I guess these are accounts that you don't want distributed widely.
I mean, yeah, I wasn't planning on it since they have like usernames and passwords and such. I mean, since I made them, I could certainly remove them or things like that, but I thought it might be nice if people could keep them if they wanted to continue using them or things like that.
Okay, so I think one thing that we can do, I see you on Discord. I will okay, now I lost you again, because we can post them on Discord and then I will delete them, right? Okay. So if you go to the tutorials channel, I will find you there.
Sounds good.
Okay.
There we go. The formatting's not terribly good on those. Yeah, that formatting's no good. Okay, so if I email it to you, would you be able to post it?
Yeah. How long do you want them to stay in this channel before I delete it?
I mean, it doesn't matter too much to me. I was just so the other tricky thing is I created about 50 or so that I was going to distribute to one to each user. So it's a little bit hard to know how people would coordinate to fetch each account. I mean, they certainly, I guess, can use the same account. It's not a huge problem, but I've been imagining one per person, but it's probably not a big deal. Not a best practice by any means, but not a big deal here. I'm sending you a file of all the user accounts that I created, so one account per line. If you wouldn't mind posting them in Discord or making that available so that people can follow along, that would be fantastic. Not to just defer it to you, but if you could take care of that.
Yes.
That would be cool.
Yeah, we definitely can do it. How about the attendees? If you really want one, if you know, since Brian said you can keep the account after a while, if you really want one, post your request in the tutorial session. We'll do a one-on-one quickly. I don't know how practical it is.
Awesome, thank you. All right, so so without further ado, I'm going to start jumping into this the tutorial or the hands-on portion of this. So so I'm going to go to editor.deepforge.org, and then this should pull up a login page here, where if you are following along and you have one of the accounts that I just or if you have one of the accounts from the or that we created for this tutorial, feel free to, of course, enter these credentials in here. All right. So when it first loads, you'll see that there are a bunch of projects that have been created here. Yours might be empty, but we're going to start with this starter project.webgmex file. So if you first just download this this WebGMEX file, and you can say create new, and I'll call it ADS20. All right, now I'm going to import it from a file. And if I just drag and drop or click the file icon, I should be able to select this starter project.webgmex that is available in this GitHub repo where I put all of the links. I'll try to I just posted the link in Discord. Oh, but it's the social channel. Okay. All right. So, anyway, if you go to this GitHub repo, you should be able to download this WebGMEX file, and then that's the file that we're going to create our new project from. So we're going to type in some name for it, select import, select that file, and then create it. All right. Now, the first thing that so I'm first going to talk a little bit just about an overview of this environment and what you're looking at to try to hopefully make it easier to get your bearings. And then we're going to start jumping into this example project. So when you first load DeepForge, we'll see things like our user account showing up in the top right. And at the top, we have this kind of bar that'll give us all sorts of project management options. So we can do things like manage projects, create new projects, import projects. Now, view compute, we'll see in a moment. But that lets us basically monitor some of our compute infrastructure. And then we'll also see that we have some options here about project history, which looks pretty bleak right now. So we just imported it. So there's nothing really interesting here with just one branch. And we'll get into some more of these in a moment, but and then a bunch of basically version control options under master. So this is saying essentially that I'm on the A-20 project on the master branch, and I'm currently looking at my pipelines. So on the left side here, we have a sidebar. And this is used for a lot of the navigation between some of these high-level concepts. So if I hover on them, we'll see that it shows a little text that tells you that this first one is our corresponds to our pipelines that this project has, which we currently don't have any. The second icon here is our executions that have been defined, that are available in the project. So as you might guess, given that we have no pipelines, we certainly don't have any instances that we have executed. We also have some resources. There already is one created here. So this is actually where we can find things like our neural network architectures. Now the name is a little bit generic, and I can explain the reasoning for that when we get into the advanced topics portion. And then as we continue down, we'll see like an artifacts index, which basically shows us any basically anything that actually has like data associated with it, or like a file associated with it. So this would include like training data, testing data, like a trained model or trained model weights, things like that. And then we have some other things that are just more of like Python modules, for example, like if you want to have custom utilities that are not specific to a single operation, as well as some serialization things, which we don't really need to get into right now. So for the course of this tutorial, you can kind of ignore these, but they certainly can be useful when you start digging into when you start digging a bit deeper than we'll go on this tutorial. All right, so let's start by creating our first pipeline. So when we go back to the pipelines index, if we click in the lower right here, there's a create new pipeline button, and that'll pop open a pipeline for you. It'll say click to add an operation in the center, and we have the name in the top left. If I do something like select the name, or click on the name, I can rename it to like, I don't know, maybe training pipeline. Actually, we'll start with something even simpler. My first pipeline. All right. So now if we can either click in the center to add an operation, or it'll give us an option of what operations have already been defined for this project, or we can do the same thing from the lower right corner. But in this case, we can start by creating a, let's start by making a pretty simple pipeline, just using some of these existing operations. So I'm going to say get CIFAR10 data, or CIFAR10 data. And now when I click on that, I see that we have an operation here that is right now the entirety of our pipeline, but of course we might want to add a little bit more. So if we select this get CFAR10 data, we can do things like hover on these blue icons, which are ports showing what the outputs of this operation are. So we can see that one of them is training data and the other is testing data. In the top right, we can hover, we can see that this lets us edit the operation definition. And we'll get into that in a moment, but let's not worry about that just yet. If we go to the lower right and click the plus icon, we'll see more operations pulled up that we could add. So let's add a training operation and a scoring operation. And how about we add an output as well? All right, so when we hover over the training operation, we see that it takes training data as input and outputs a model. Our scoring operation takes data and a model, and our output operation takes just some data to save, or save data. So we might want to connect our get CFAR10 training data, or that output, to the input of our train data operation. So I can see we're going to train on the training data as you would expect. Let's click on our model output and specify that that is the output that we want to save. And we can name it like, I don't know, maybe model. So yes.
Can I interrupt for there's a question said, well, where do we need to go in the interface to actually add the new project from the web Gmax file?
Yeah, no problem. Thank you. I missed that.
I don't understand the question, so I'm just reading it.
Yeah, no worries. Thank you. I missed that one. So when you first open editor.deepforge.org, you should get this projects list. And if you click create new in the lower left, then you can name it. Let's see. Okay, so you can name it like my new project. And when we hit create, now we can select import and then click on the little file or drag and drop it. All right. There is no create new button. Let me check something quick. This should... Let's see. We should be fine. You should be able to create things. Let's see. All right, let me take a quick moment if people don't mind. Oh, wow, why don't you see it? You should be able to create them. All right, one quick moment. Are there, any, like, hopefully people don't mind me trying to quick debug this. It looks like it is a issue that multiple people are having, so I want to make sure that people can kind of follow along. So if you aren't having it, or just let's go one. I don't know why. Can someone share their just username so I can try to make sure that I'm okay. Perfect. Thank you. All right. Password. All right. So. Oh, why don't you see a create option? Okay, going back here quick. Geez. Sorry, can you try it again? Yeah, sorry, that was my bad. So let's see, thanks for posting these questions. I want to make sure you guys can follow along. All right, it works now. All right, so who else is, thank you. All right. good news is that it's an easy fix. The bad news is that I should have caught this earlier. But I appreciate your patience, everyone. Cool. All right. There should be. All right. All right. Okay, so yes. So I feel free to keep posting any usernames that might need this, and I'll just hop over and do it periodically as I'm continuing with the tutorial. Just so we're not all waiting. All right. So, okay. So I'm going to hop back to my project. There we go. 17, 20. All right. Okay. So so I apologize for that hiccup. Everyone who has posted a username should have access now. So so if we go back to our first pipeline that we were creating, so just for anyone who is following along, we were like fell behind because they weren't able to create things. We click create new pipeline in the lower right corner, and then we can name it by clicking on the text, and then kind of go from there. So we clicking on the lower right corner lets us create new operations or add operations here, and then we can add our get CFAR10 data operation, our train operation, our output operation, and our score model operation. And once we've done that, we can hover on it, or hovering on the one of the output ports that gets CFAR10 data, lets us know which one of these is training data and testing data, and we can connect our training data to our input to our train operation. Our output, which produces a model, we can connect the model or specify that the model is an output or pass it to our output node. This lets DeepForge know that this is some data that we care about, and it'll be saved back to DeepForge. And if we select the output node, we can name the data accordingly. So like whatever we would like it to. So in my case, I just wanted to save this as model. And now we can look at how we can just incorporate this score model operation. So it accepts data. So I click on this data port. I want to connect that to the test data coming from get CFAR10 data. And then the model that's passed to score model should be the output of train. All right. Oops. Now at this point, we've connected at a high level this kind of flow that we want our pipeline to follow. But if we select train, we can see that it expands and it has a few extra parameters. So like shuffling, the number of epochs, the batch size, as well as the model. Now I'm going to turn the number of epochs way down, just so that we can get a feel for how this works, but not necessarily need to wait for 100 epochs. So I'm just going to set it to 5 or so. Actually, let's make it a little bit longer. Let's just set it to like 10. And then it also has this model parameter, which is currently set to none. Now, if we click on where it says none, also everyone who's posted their username should have create permissions now. If anyone doesn't, please repost it or ping it again, or in case I missed any, and I'll be sure to fix that. So when I select this none option for the model, so I want to change it from none to an actual architecture, I can select MLP. Now MLP, if we recall, is the one that we saw in passing under the resources category. Now we can look at this in, we can look at this in detail right now. Basically, this is, if we click open under MLP here, we should see, let's take this up. We should see that it, all right. Over here, not sure why. So if you click on MLP, you should be able to see a there we go, and an architecture, so a neural network architecture. It's this one's very simple. So just as a little bit of background, in case you're not, in case you haven't or aren't familiar with CFAR10, it's a data set that consists of a bunch of images. It's an image classification problem. So you get a bunch of small images like these shown in the on the left here, and they belong to a number of different categories, like truck, ship, and so on. There are 10 categories that are shown here, and each of these and the task is to train a classifier to predict, given an image, what class it belongs to. Now, this first model here is very simple. It's not, it's just flattening the data. So losing all of the spatial information. And then it's just passing it through 2 dense layers to get the output. Now, if we hover on the connections here, so like in the pipeline editor, selecting any layer will expand it so we can see any of the parameters. So selecting it will show any of the parameters that we might want to edit. So in this case, we can see that the input shape is 32 by 32 by 3. And that corresponds to the size of these images. So 32 by 32 and their colors. So there are 3 channels, RGB or red, green, blue. And if we hover on any of the connections coming out, we can see the shape of the data. So as you'd expect, the batch size here is unspecified, but then the rest matches. So 32 by 32 by 3 color channels. And if we select things like the dense, or so once we flatten this, we can see it turns into a just a vector of 3072 scalar values. And we pass that through a dense layer that has 512 units and a bunch of, and also an activation function specified. You get 512 outputs. And then finally, to do our actual classification, we have a dense layer that has 10 units, 1 for each class. 27. 1 for each class. And we're using a softmax activation function, which will ensure that the output is a probability distribution. So now, as you'd expect, the output corresponds to the batch size, so the number of images passed in that batch, and 10 values, the probability that it belongs to each of the 10 classes shown here.
Excuse me, Brian. There are a
yes.
few posts in the Discord said they cannot see the project.
Yeah, I'm trying to keep up with them while I talk, and it's.
Okay, yeah. Take your time. Sorry.
Yeah, no, it's all good. I'm doing number 3 right now. and 14 I think is done. I think so. So I think everyone should be caught up. If let's see. If not, again, please post again. And again, thank you again for your patience. I apologize for this hiccup. 14 still won't work. Let's just double checking that. All right, let's see. Can you try 14 again?
There's a question I'm going to read for you. I assume all these predefined resources that we are accessing were pulled from the initial loaded project file. The form of the MLP model was defined there.
Yep, exactly. Yeah. So it was defined there. I wanted to get us started with this kind of simple model. I figured as we continue, we can define a convolutional layer, but I wanted to start working at a level where we where a lot of the operations and architectures are there and we just need to piece them together. And then I was hoping that we would get into like creating our own operation, creating our own architecture, and kind of digging into a little bit more of the details. But yes, exactly. These were all defined in the starter project right now. Let's see. 27, 7. Okay. All right. Is 14 working? I saw that. Oh my goodness. I apologize for that noise. The challenges of doing things remote and from home. All right. So, okay. I'm going to double check 13, and then I think everyone should be. Oh, 13 I missed. Sorry. And then everyone should be hopefully up to speed. Okay, so, all right, so now everyone should hopefully be up to speed. Again, I apologize for these hiccups. So this is a really simple model. As you can see, we just pass some data in, we squash it down to be a single dimension. So again, losing all the spatial data, just concatenating all these rows. And then we pass it through a couple of fully connected layers and produce the output. You'll notice that when we click on some of these layers, like this dense layer, we have this question mark. Clicking on this will give you some documentation about what the layer does. So if you have any questions, this will do things like try to give you some feedback for these. They periodically for like dropout and things like that. Like dense is a pretty common layer, but for some of these others, they will include things like links to the paper where this was introduced and other useful resources like that. And all of the layers that are supported in the current release correspond to all of the layers supported by Keras version 1. We do have an updated version for Keras version 2, but it just hasn't been released just yet. Okay, so this is the architecture that we have defined. If we defined a new one here, that one would certainly show up as another option when we were specifying the model to use or the architecture to use when we trained our neural network. So now clicking on the rest of these layers, we can see that we have none of the others have any configurable parameters. So now at this point, we have one of two choices. One option would be to export the pipeline. So this would download a zip file of this code that would let you basically give you all the Python code to actually do these tasks. So this would download the Python, or this would download Python code that would first download the CIFAR10 data. It would have a reference to the neural network architecture that we created visually, and then train it for 10 epochs, using batch size of 32. And I believe it would save the output as a file, because that's when you're running from the command line, that's the most natural thing to do with outputs. Now, in our case, we're going to just try to execute, or we're going to execute it from the browser. Now, I mentioned before that, I believe I mentioned in the abstract for the tutorial that we were expecting a SciServer account, or the users to have a SciServer account. So, so if you haven't used SciServer before, you can access it at sciserver.org. You can create a free account, and this is all hosted by Johns Hopkins, again, trying to accelerate and facilitate science and in the natural sciences broadly, I guess. Okay, so this is what I'll be using here. They have a lot of different, so this is, they have a lot of different infrastructure capabilities, like storing big data sets or actually executing code for you. So they provide like compute resources and such. Now, when I click on this execute pipelines button, it'll pop up and ask a few different options. We have 3 categories of options, really. One is the basic options, like do we want to name this something special? This is optional. Debug mode, we don't really need to worry about that just yet. And then we get into this compute options category. So now under compute options, we get to pick where we want this code to run. So what infrastructure would we like to use for to run this pipeline? So we have 2 options right now. One is WebGME executor framework, which there might be it'll probably be better to have a better name for that, because a lot of people I think might not be familiar with WebGME. But that's the framework that DeepForge is built on top of. And this executor framework essentially lets you connect your own computer to DeepForge. And we have a read the docs. I really thought it, there we go. We have a read the docs for DeepForge that'll explain how to get started with this. If you want to like connect your own GPU, but still use DeepForge for trying to build a neural network architecture and define your pipelines and things like that, but again, want to use your own compute, you can certainly do that using the WebGME executor framework. For now, I'm going to use SciServer compute. And right now, we are working on we're working with the SciServer team to have a better sort of integration where we can have things like, hopefully, like API tokens or access tokens like you see on GitHub or with other like app integrations to things like Slack. But at the moment, unfortunately, we just have to pass their credentials here. Now we can select a compute domain, and this is a configuration option that's specific to SciServer. So I'm going to run on the small jobs domain. And then for storage options, this is basically defining when we do things like have an output, or if we potentially need to save any intermediate files, where should these be saved? So right now we're going to specify SciServer files again, and I will repeat my credentials here. Now I'm going to use Scratch storage, which might be deleted, but since this is just a tutorial and I'm not too attached to the output of this pipeline, I'm going to use this temporary volume pool, and then say the volume I'm using is my username /Scratch. But of course, as you can see with these other storage options, you could certainly have your own personal S3 server and have your own GPU machine, and wouldn't have to be relying on SciServer here. But since I have an account and it's already integrated nicely, I'm going to use this. So now once I've configured the compute options and storage options, I just click run. And now in the lower left, you'll notice that we have this one associated execution area. If I select that, it'll say, we can see that there is an execution that was created today at 12:36 my time anyway. And if I select my first pipeline execution, we'll see the associated execution. Now, like we saw in the slides, this is basically a snapshot of the pipeline that we were working with, but it's showing the state of the execution. So if you noticed before, this get CFAR10 data operation was kind of a light gray. Now it's turned yellow, or it was a light gray because the job had been created and submitted but hadn't started yet. Now it's yellow because it's running. These other ones are dark gray because they're still waiting on data, and they are pending, really. And at this point, I'm going to circle back around to that dropdown that I mentioned before in passing. If we go to and hover on DeepForge, we can see this view compute option. And now this will have a little bit more context. So when you select View Compute, if you recall, when we were selecting where we wanted to execute this pipeline, we had, again, two options: WebGME Executor Framework, shown in the first tab, or SciServer Compute, shown in the second tab. If you're using WebGME Executor Framework, you can connect workers that are associated with your user account, and you would see those worker machines in a list here, and it would let you know whether or not they're idle or waiting for a job or things like that. Then you'd also have a job queue. So basically these workers would be taking jobs off the queue and executing them until everything is complete. Now, in our case, we're using SciServer Compute. So if we select that, this just basically links you to SciServer's Compute dashboard. Now I need to log in here quick. Once I sign in, we'll see that we can jump over to the jobs category. And we can see that this job that ran at 12:36 completed after 2 minutes. And now we can see that it's actually completed here as well. Oh, God. All right, so Joseph just caught an error that I had not thought about. Let's see. Okay, so so the error that Joseph sees is darn, an error in job definition message that's showing up from SciServer. Basically, let's see if there's a good way around this. I believe the issue here. Okay. Darn, that's okay. So anyway, the issue here is unfortunately I'm afraid that the problem might be that in order to run these DeepForge jobs, it relies on an image that SciServer has called DeepForge that has any required dependencies for it, and I just realized that they might only have it around for specific users. So in that case, I can create, this isn't going to be best practices, but I have another user account that might work, or I can change my account password, and as long as you guys don't delete my things, doing it kind of on the honor policy, I guess. I could share that so that people can run things. Man, it's disappointing. I was testing these things with my user, make sure that you guys had user accounts, but I didn't think about special privileges that my user account might have that wouldn't be available. Yeah, so I might, yeah. So
How about we continue?
Yeah, I think that's a good idea. I think I'll continue, and if people just want to follow along then, and you should be able to create these things, but you might have difficulty executing with this error in job definition error message. Then I'll circle back around to this once we complete. Okay, so now as I showed before, we executed this. We can see that first job has completed. Our second job is running. It's been running for a couple minutes. This is this train operation here. If we select this job that is finished, we can do things like view the output. This one won't be terribly interesting because it's just downloading something. But when the train operation completes, we should be able to do things like view a plot of the loss during training. Which is just using your standard matplotlib, but since matplotlib supports custom backends, you're able to kind of provide the same interface but different behavior where it integrates nicely with DeepForge. All right, while this is running, I'm gonna let's see. We have two different directions that we could go. One would be to wait for this to complete. Or would be to start building a convolutional neural network here, which might be the better approach. And then the second would be to explore some other pipelines that have already completed, just so you can see how they look and how you can view the feedback and things like that, so you don't have to be waiting here too much. Does anyone have any preferences? It's always hard to be interactive when we're doing things remotely, but I will show a completed job then, actually, while this runs, just so we can still stay focused on the execution portion of it, and then I'll hop over to a neural network architecture itself. Creating a convolutional neural network architecture. Or let's see. So if we hop over, I have another one. While this one completes, I have a okay. So like we can look at this other project, which is used for doing things like redshift estimation. Now in this one, there are a lot of different pipelines that perform a number of different tasks. We don't need to get into the details of these too much at the moment, but if we look at like the executions tab, we'll see that actually let's pop open one of these executions. We see that we can have other pipelines for doing things like in this case, what we're doing is we're trying to look at like a learned feature space. So given a data set and weights for this architecture that we're using here, it'll compute the errors and then pass in the embedded features as well as the learned features as well as the errors used by this network, and then it'll visualize them. Now, like before, or like we saw in our tutorial, or our hands-on walkthrough, which will be finished in a moment, and we can show the analogous things there. We have this view output option. Now, when we select this, we can see things like the logs on the right here. Now, in this case, this one was actually run in debug mode, so it actually lets you see the code on the left. So you could edit the code and rerun just this job kind of iteratively while you debug things. If we look at visualize embeddings, this one will be again, this whole pipeline is in debug mode, so we have the code on the left. Otherwise, we would only see the content here on the right. But we can see the standard out and standard error shown here. And if we select graph, it'll show you the plot that was generated right here using matplotlib. Does this make sense to everyone so far? Now, I haven't explained the content of this plot, and I'll explain that in a moment, but just showing a little bit of when we're exploring these executions, being able to view the output as like a log output or graphs or plots and such. And then also mentioning that if you're executing and also using this execution as an example of running an execution in debug mode, where we can edit the code here on the left and then just rerun it, or we just ran ours in as a snapshot. So just so no debugging capability like this, but we know that, or basically making it so you can't change the definitions of the operations afterwards. So, so at this point, let's see, I'll over here. So it looks like my job is still running. So it's still training. Maybe I should have turned the box down a little bit, but at this point, I'll mention a little bit more about what we are visualizing here while we wait for this job to finish. And if it isn't finished by the time I finish explaining this pipeline and some of the things that we're exploring here, then we can just continue on and start looking at a new network architecture. But essentially, when we look at these executions, if we go to the executions tab and we select one of these executions that we have run in the past, we can see any of the plots that were shown from that execution. So we see that this one has kind of this swirl, which I'll explain in a moment. Or we could do things like select this one and this one. We can see another kind of 3D plot. And of course, you can kind of compare them side by side. But basically, what the goal is here is to make it easier to compare across executions, where you might have different, you might have different experiments running with different parameters or different things like hypotheses you might be testing. Now, to provide a little bit more context of specifically what this one is looking at is, is everyone here familiar with like dimensionality reduction and seeing examples of things like t-SNE applied to MNIST or digits? Or sorry, MNIST or CIFAR10 or some of these other data sets. Okay, sounds good. So yes-ish, sounds good. All right, so so if we, all right, so first I'm going to explain a little bit about dimensionality reduction. So basically, there are so you can find, so MNIST is another data set like CIFAR10, but it's just handwritten digits. So specifically, it looks like you see images like these. So they're just black and white, and you just have numbers that have been written. Now, t-SNE is just an example of doing what they call dimensionality reduction. And the goal in dimensionality reduction is you have some data that's really high dimensional, and you would like to convert it into a smaller dimension, or you'd like to, I guess, map or project each of the points to a lower dimensional space where you're preserving some of the characteristics of the whole data set in the higher dimensional space. So for example, t-SNE is like stochastic, or no, sorry, forget what the T stands for, but basically what they're trying to do is preserve the number of the neighbors. So if, in other words, if you have this data in a really high dimensional space, you would like to convert it into a bunch of data points in a low dimensional space where the neighbors, oh, here, T distributed stochastic neighbor embedding. Here we go. You'd like to convert it into a data set in a lower dimensional space where if 2 points are close in the low dimensional space, they're close in the high dimensional space, and vice versa. 1 second. So some people have used things like t-SNE to just apply directly to things like this MNIST data set. And one thing that you can find is that the data points can end up being kind of clustered together around similar values. So we can see, like in this case, that the 5s are this kind of light neon green. And so all that they did here was they just took the MNIST data, so the pixel data from these images, put in that's flattened down to a single long vector, and then they just tried to represent this data in a 2-dimensional space where values that are close in the high dimensional space are close in the lower dimensional space. So the interesting thing here is that this that when applying it to this data set, you see these kind of clusters based on the classes. So the number, the handwritten 2s are generally in this purple in the lower right corner. Handwritten 6s are in the right, blue or light blue, or 3s are in the top right, this light blue color, and so on and so forth. Now, the reason why we started talking about dimensionality reduction is that it's really well, first interesting to see how they can be so separable, and it gives you a little bit of a way to look into the representations, or the raw representations, so to speak, of your data. Because if these points are again close together in the high dimensional space, they should be close together in the lower dimensional space. And if they look linear, like really separable or easily separable in the lower dimensional space, it might make you feel a little bit more optimistic about the problem as a whole. Whereas if these spaces, if these are really mixed it might mean that this problem is a bit harder or more challenging than otherwise. So in this project, what we were looking at was the an embedding, or we performed dimensionality reduction on spectral data from galaxies. And we were trying to train, and we were interested in doing redshift estimation. So trying to train a neural network to basically predict the redshift values. Now, really, the goal was to output like a probability distribution of the redshift values and then take the expected value. But it essentially still boils down to doing redshift estimation. So we in this now these executions, there are a few different ones. Now the one that I'm showing right now produced one plot here, and this plot shows you the original image data. So this is the original, I should say, spectral data, because some of it might be outside of like visible wavelengths. But these are this galaxy data for, so each point here represents a galaxy. And we took the original data set and then just tried to, again, project it into a smaller dimension, preserving the neighbors. So points that are close here should have been close in the higher dimension. And then we colored them by their redshift values. So really low redshift values are really dark, as you can kind of see in this little bit of a tail here. Really high redshift values are much lighter. You see we have a few outliers kind of in these corners, but we have many points. It's not quite as satisfying as looking at the MNIST data, where it was really linearly separable and we saw this common smooth pattern. All right. And please jump in with if there are any questions. I realize that it's always much more challenging to get feedback, engage feedback, and I know when we're doing these things remotely over screen shares and things like that. But if there are any questions, feel free to venture them. But so essentially in this case, or in this project, we had trained a neural network to do some redshift estimation. But then one of the questions that we had was basically, did it learn a more meaningful representation of the galaxy spectral data? So in this case, and actually looks like the other job has completed, but I'll finish up on this thought first before we hop back. So in this case, we looked at the original input data and just tried to do just dimensionality reduction, hoping that we might see some nicely separable or a nice gradient over a common pattern. So we see some structure in the data that is correlated with the redshift value. After doing just this dimensionality reduction, again, just like we see when we were applying t-SNE to MNIST, or this dimensionality reduction technique to handwritten digits. But as you can see, there's some, like we see some, again, low redshift values together, but then the rest seems kind of just a big mess. It's a lot harder to gain any insight from. So then the next question is, what if we looked at so a neural network with all these layers. Wait 1 second, please. So a neural network. Like the one that we're training here. You could view this as the first few steps. This one doesn't have very many, but all the layers except the last one. So this one was the one that converted it into a probability distribution. So you can view a neural network as everything but the last layer, being learning how the representation or feature learning, or representation learning, I mean. So like learning what features are important and learning a good representation for your data. And then the last layer just being a linear classifier in this more meaningful space. If we view it that way, one thing we can do is we can feed the data. Actually, I'll extend this guy for a second. We could feed the data through the network, all except the last layer. So we could just remove this last layer, feed it through everything up until then, and just try to look at what it learned or what the space looks like here to see if it, the new representation that the network learned captures some or is correlated nicely with the with whatever we care about. So in other words, is it linearly separable between a number of classes, or is it correlated nicely with the with like the redshift values, for example, in the case of regression? Now, if we why does this look so so one thing we can do is we can hop over into like, let's see, is this one? So we can take all of our input data and we can feed it through this this neural network that we trained, all except the last layer. And in doing so, this should give us a nice, and then we can see if we end up with something where the space seems to show some sort of structure with respect to the value we care about, in this case, redshift value. Okay, so I don't hear any questions yet. I'm hoping it's not because people just don't know what to ask, but it's because they follow, they understand everything. But anyway, so so in this case, like if we look at, for example, this plot, this is taking the learned features. So it takes the neural network architecture that we trained to do redshift estimation. It feeds all of the training data through it, except it doesn't. It stops before the last layer when it actually does the prediction task, or the, again, because you can think of the last layer as a linear classifier on top of the in this more meaningful vector space. And then we just did perform dimensionality reduction to try to look at what the data set looks like in this space. So here what we can see is this, so again, color-coded by redshift value. So we can see that the really low redshift values are kind of all up here together. And we see a little bit of a nice gradient actually as it flows down and around, and kind of, again, with this kind of like sort of almost brain shape, or when it comes down to the brain stem, I guess, we start getting to some of the highest ones. But it makes you feel a little bit more optimistic that it learned a meaningful representation for your data while trying to perform this redshift estimation task. All right. That said, I'm going to hop back to the execution that we kicked off in our hands-on example. When I look at the executions tab here, I can see the plot that was generated for this data set. So for this data, or when training on this data set, so when we train on this one, we can see that it produced this plot that says training loss. Here's the cross entropy loss, trained for 10 epochs. And we can see that it was going down and still going down pretty steadily. So we didn't train nearly enough because it certainly hasn't converged yet. If we click on the name of the execution, we can see that the execution has completed. We can certainly view any of the outputs for any of these guys. And then we can view like the console output or any plots that were generated for this execution. All right. So this was basically trying to, so again, the goal here was to start with some existing operations, see if we could train a neural network architecture by just composing these operations using this off-the-shelf architecture, which is a very simple architecture, and then just run an experiment where we again were saving this data, or saving the output model. Now next I'm going to start digging into customizing some of these operations and architectures, and customizing the architecture to use like a convolutional neural network instead. But before we do that, I want to make one last comment on the execution that we just trained. So if we recall, so when you look at this execution, we see it all trained. It says even the output operation completed, and it was saving it as model. If I look at this output, it says it was about to save the output artifacts. It saved the output data to SciServer file service. and saved output data to SciServer file service. But if we hop over to the artifacts index, which we showed earlier on, so that's the fourth thing down here on the left, we can see that now we actually have an artifact that we have generated, and this was the one that was the output of our training pipeline. This is named model. We know what type it is, the size, when it was created, and if we click on this information icon, we can actually see like some of the raw details about what it is and where it is and things. And we can certainly confirm this by checking that this file exists on SciServer, or we could just download it, where we need to authenticate one more time with the backend that it's saved at. And if I authenticate with it, it'll say that it's fetching. Now this is a not huge file, but big enough where it will take a minute. There we go. And now we see that the file has been downloaded. So now we have our, and then where this file is our again trained model. All right. So is everyone with me so far? I feel like I've been going kind of quick and haven't heard a lot of questions yet. I feel like maybe there should be questions. Cool. All right, it's following so far. Awesome, great. Great. Oh, I do really appreciate the feedback. It's sometimes so hard when you're again doing these things remotely. So in that case, we've created our first pipeline. We ran through and trained just a simple architecture. Now let's create another pipeline. Let's say to just look at the distribution of training data over the different class labels. So in other words, let's inspect our data set a little bit, because I recently heard a sort of, I guess, joke or criticism of a lot of machine learning tutorials where they say that when you're learning about it, you're usually grabbing some benchmark data set like MNIST or CIFAR10, and you train a model and you get 99% accuracy and move on. Whereas when you're working on like a new data set or trying to apply it to some specific task, oftentimes there's a huge amount of trial and error and understanding your data set and trying to understand how these things in your data set impact the trained model. You know, when you're struggling with things like mode collapse and such. So I think although we're still working on the CIFAR10 data set, so it still will, there certainly aren't going to be things like class imbalance issues because it's already been carefully curated. It still might be useful to, or a nice little exercise to visualize again the amount of the data set that's across these different classes, so we could understand if there was class imbalance while also, of course, learning how to do a custom operation. So I'm just going to call this maybe inspect data. And again, even if you're unable to run these pipelines, you should still be able to create these operations and such, so that we can hopefully run them once we get to that point and have some time to debug them. Or of course, you can always export it and run it on your own computer, like locally. So so now I'm going to create a node. I'm going to use get CIFAR10 data again, and then now instead of, so we only have trained score model and this get CIFAR10 data operation, as well as the input and output. So we're going to actually create a new operation here. Now, when we create this new operation, this opens up the operation editor. So the operation editor will basically let you define your own operation. It shows the code here on the left, and it shows the interface to the operation here on the right. Then it also, you'll notice there are these tabs on the right-hand side. You can also select the environment, and this basically lets you define a conda environment file if you have custom dependencies that are maybe specific to your domain or specific to your current task that you could specify here. If you do this, when your operation runs, it will, before running your operation, it'll make sure all of your dependencies are installed, and then of course run the operation code. Now operations are defined using using basically this, or by defining a class. which has this execute method. So I can change this to like visualize data. Now I can see that when I change it here, or change the name of the class here, the interface automatically updates to say visualize data. Now our visualize data operation is going to take some data set. So we could certainly add this as an input parameter to execute, but I'm going to add it here. Actually, I'll add it here. I'll add it on the right side. So data. So when I type data, now we can see that the data shows up here on the right-hand side as an input to the visualize data operation. And I certainly could delete it, and it deletes from the right-hand side as well. So here, if I add data, now I can see that data is back. All right, so basically what we're going to, let's make a little list here. So to do visualize the data set distribution, so distribution of labels in the data set. All right, so if we're taking data here as our input, one thing we can first do is we can just hop back and just double check what it looks like when it's coming from get CFR10 data, because I never really looked at these internals. Now, I mean, I could be a spoiler and just say that it comes in your standard kind of Keras format, but I don't know, no one really likes a spoiler, and we can just verify, I guess. So basically, we can see that this gets CFR10 data operation, which I looked at the internals of by clicking on and then selecting this button in the top right, edit operation definition. We can see that when it runs, it uses Keras.datasets to load the CFR10 data set. And then it converts the data to actually be one hot encoded rather than just being the index of the class. So, and then it does things like just make sure that the data, so that the image like pixel values are all between 0 and 1 rather than being 0 and 255. So we can see that it returns test data and training data, which are these tuples of X test and Y test. So if we want to just pass our train data to this visualize data operation, that means that we will actually probably want to get the Y labels from it. And that will be the second thing in the tuple. And once we get our Y labels, or Y, I should say Y values. All right, so these, since it was calling these are one hot encoded. So we probably want to actually take the argmax using NumPy, because this will convert, of course, the one hot encoded vector into the index of the 1 in the vector. Import, and we'll need to import NumPy, of course. Okay. So I'll also need matplotlib. Since these ones are pretty standard packages, so these ones don't actually need to be defined in the environment tab. Because these are already kind of a part of your standard suite, I guess. So, all right, so now we can do things like, once we have all these Y values, NumPy has this function called unique. So you can take unique of the Y values and then return the counts as well. And this should return 2 values. First one just being the actual unique values. And then the other one, the second one being the counts for each value. All right, so I saw there was a question that I just saw now. Is all dependency management handled via Conda when building operations inside DeepForge? So right now, Okay, so yeah, this is handled with Conda. There is some customization that can be done, especially if you're running your own like DeepForge deployment, because you certainly can run DeepForge locally, like a Jupyter notebook. This is more in the advanced topics section that I was going to mention towards the end, because and anyway, if you're running it locally, and you can certainly add things to the base image to like to the base Conda environment. So in other words, in DeepForge, we kind of layer Conda environments. You have the standard like worker environment, and then you make sure you install any like operation specific like dependencies that are specified by that environment file. So these things could certainly be customized, but it would probably have to be at depending on exactly what you want to do. I mean, if you wanted to add things to all to all operations run with that deployment, you could certainly do that. But I'm not sure what extent are you thinking about customization, Joseph? Gotcha. Cool. Yeah. So yeah, I can circle back and get into more of the details later. At a high level right now, basically, there are a couple layers of these. So like you can extend DeepForge. Okay. Actually, I might save this for a little bit later after we do the custom operations. It's a good question, and I'd love to go in more detail, but I just want to make sure we get through this stuff first. So hopping back to this this custom operation that we're writing, we first can get the unique labels and the counts for each of the Y values in the data set, or the training, or whatever data set is provided, be it training or testing data. And then now we can plot these by just saying like plot.bar, unique, and counts. And then of course we want to show this, and this should be basically all we need to get started. Now, as one last thing, not that it's super necessary, but I mentioned before, but this like we've seen before, like in the train operation, that these operations can have custom attributes or like parameters that can be customized while you're building the pipeline. So we can specify those by clicking in the interface editor here, new attribute. And now we can say that I want to add maybe a title to the plot. And when I save this, we'll see the code updates automatically to have a constructor. And we're going to set self.title to title. And now we can update our plot to plot.title, self.title. All right. Now we can just return to the pipeline that we were working on. And we can simply pass, say, like the training data to visualize data. And we can, as I set the title to, let's say, train data class distribution. All right. And then now if we just wanted to run this very small, pretty simple pipeline, we just, like before, click on the button in the corner, and then just to specify what compute and storage resources we would like to use. I'm just going to keep using my kind of scratch storage here. And as before, we see this one associated execution shows up. Again, it takes a moment because we it gets put in the queue on the SciServer side. So some of these things certainly depend on infrastructure that you're using and so on and so forth. But in a moment, we'll see, there we go, that this job is started. It might have to configure the environment beforehand. And now some of these things will be faster or slower depending upon like the infrastructure that you're using and whether or not they have like ephemeral, these kind of like ephemeral containers that get spun up and might need to be reconfigured more or less than before. So there are a couple little things like that that can certainly play a role into how fast or slow this portion is. Certainly if you're running it locally and running it like a Jupyter notebook where it just basically spins up a sub process, like or on the server, which in that case would be your own computer, then it's certainly much faster. But of course, there are trade-offs to different infrastructure backends, and DeepForge's goal is to kind of abstract above those, so that you can, so that it can try to focus on the problems of like modeling, for example, your neural network architecture and some of these challenges, and not necessarily getting stuck up on the and giving you the flexibility to download your code in an executable format or just run it in arbitrary locations and things like that. All right. Now, now we can actually hop into like making a new neural network architecture, since right now we first took some operations that were pre-existing that were already defined for this starter template and composed a pipeline out of them. And then we extended it a little bit more by adding our own operation that we wrote from scratch. And now we can actually just try to customize this by actually defining our own neural network architecture. So here we, if we go to the lower right under the resources tab or category here, we have this create new architecture option. Now, when we create a new architecture, I can name this convnet, and let's add a new layer. Now, as before, we know that the shape is 32 by 32 by 3. Now this will go away in a moment, but initially I didn't have a shape, so it was showing us that error still. And now if we select, you can either shift click on the arrow at the bottom of the layer, or you can click in the lower right, or there are a few different options here. So let's see, shape's provided. I'm not sure why it's still there. Should go away in a moment. So we can add a convolutional layer, a two-dimensional convolutional layer. There we go. There's a little delay when it updates for errors and such. It'll show a new error here in a moment. But so now you can see that we're getting 32 by 32 by 3. We can do something like 32 filters and add like a kernel size here. And let's add an activation as well. Let's throw together a small convolutional layer, or convolutional neural network. So add another convolutional layer. All right, so we just got a notification saying our execution from before finished. I'm going to finish configuring this second convolutional layer, and then I'll hop over and check it out. So I'm going to add another. So basically, just duplicate the essentially configure it the same way as the prior layer. Not sure why the feedback is so delayed now. Usually, it's not quite this delayed, but I'm going to put this architecture on hold for a moment as I hop over and check out the other execution. Now, there is one little so one little thing that has sometimes happened that I need to straighten out. It's a kind of a minor, like not a serious bug, but just kind of an annoying little one. Is you'll notice that when you hop over to these executions tab, it says that it's still running, but that's because it thought that since I was working on the project and it was working on it, that these were, it wasn't sure. I'm not sure why I thought there were conflicting errors, but either way, it ended up forking itself to its own branch since it saw that I had edited the project while it was editing it. So if we go under ADAS here, or the name of your project, whatever you named yours, we can see that it forked back here. So I created a new architecture. Oh, sorry, I'm looking at the history of the project now. So I mentioned before that the whole thing is version controlled. So these were my edits to add the new architecture, and it forked its execution right there. So if I hop over to this fork, now we'll see that it knows that execution or inspect data has finished. Selecting it shows us the plot that was generated by this execution, but we can of course just hop over and look at it. And view the output here, where the graph is 5,000 of each of the 10 classes. So again, this one's a perfectly balanced data set. As I mentioned before, it's this one's already carefully curated, so it's not the most. So we're not going to really run into any problems here, unfortunately, I guess. For this, but I still wanted to at least show a simple example of how you could create your own custom operation to do to start like exploring data and plotting and generating these plots that DeepForge can detect, which it detects automatically just using matplotlib. All right, so now I'm going to hop back to the master branch since that one had kind of forked to there. And okay, so okay, so I did see a little error pop up. I'm just going to refresh quick. So just to be cautious, I don't think there's anything important, but anyway, now if we hop over to this convolutional architecture, now we can add a max pooling layer. Some pooling layers here. Let's do some max pooling. Let's do it 2 by 2. All right, and then no, let's drop out, flatten, and let's now let's start making it just a fully connected portion at the end here. So trying to do some, we'll learn some meaningful features from the images, and then add some fully connected layers with some dropout just to try to, just for some regularization, so it hopefully doesn't overfit. I don't want that one. Dense, dense, dense. Now, this output node is optional, unless you have multiple outputs from the architecture, but I think it's kind of nice to add either way, or it's kind of nice to add anyway. So this dropout layer now, let's set to 0.25. Let's set our, let's configure, oops, let's do 512 here. Do again. Okay, so so once we've created the this neural network architecture as well, it should disappear in a moment here. We should be able to hop back and go back to our original pipeline. And now when if we click the X next to the model, so the training pipeline that we're using before, now the convnet should show up as well. And now we can actually run this pipeline. And we can kick this pipeline off like we did before. Not sure why it's running a little bit sluggish right now, but okay. Now, let's see when I configured this like before. Okay, now we can configure this guy, and then when we run it, we'll see another execution pops up in the lower left. And of course, this, like before, will be running on SciServer, and we should be able to see the feedback here. Training, of course, will generate the plots like before, and so on and so forth. So just as a quick recap, we started with just taking this this starter kind of template project taking some existing operations and piecing them together into a training pipeline. And then we went and wrote our own operation. While we were waiting for that pipeline to run, of course, we went and explored another example where we were just looking at different executions that were visualizing learned feature spaces as compared to the original inputs. So that was when we were looking at that redshift estimation problem. But then we came back and we wrote just a really small pipeline that was basically looking at the distribution of the classes in our training data set. And then we went and wrote our own, or created our own neural network architecture, this convolutional neural network. I kind of cruised through that pretty quick. I do have an example one that it started from. I believe it's like loosely based off of VGG, so that's where some of those parameters had come from. Then after creating our own neural network architecture, we just kind of swapped it out in our original training pipeline, and now we're executing this as well. So I made a comment in the past about ephemeral containers and such, and how that can play a role into the performance. Now, one specific case where you'll see that is in this pipeline right here, or again, just kind of a passing comment, but this get CIFAR10 data, the get CIFAR10 data operation, as I showed before, so this is the job of it, but of course the code that defines this is using the Keras datasets like API, so that it will download it and cache a copy locally. But since on SciServer they have these ephemeral containers that we spin up, certainly the cache is gone when we spin up the second container, so it'll have to actually re-download it, unfortunately, in this case. But that's more, again, a side effect of the infrastructure, that the backend that we're working with, which isn't not necessarily meant to be a criticism, just more of a comment, one of the side effects in this specific case. Just wanted to give some context for why, like, if you were running this locally, this would be super fast because it would be cached and using some of the tricks that the Keras datasets module uses. But since we're executing it on within a new container that was just spun up, it certainly doesn't have the cache from the previous execution. All right, so are there any questions at this point? You can see. All right. So if not, or if there are just any general comments and stuff too, I would love to hear them. I've been hearing myself talk for a while now, and then it's and anyway, I welcome any comments, questions, general thoughts, things like that. If not, I'll jump into some more of these advanced topics. And I'll probably circle back around to the question that Joseph asked earlier. So a couple comments. If we have a couple remaining kind of slides, some of them a little bit more high level, but as you saw when we were running these pipelines, DeepForge tries to integrate with existing infrastructure. In this case, the integrations that are enabled on the public deployment anyway are, like SciServer and S3 and things like that. We'll see them more in a moment. But if you run it locally, you can certainly run it like a Jupyter notebook, so it runs much more quickly. There's no queue, it's just spinning it up as a sub-process and such. But anyway, these integrations are supported through the use of compute adapters and storage adapters. So these basically convert the jobs that are defined in DeepForge into something that can be executed on whatever the compute infrastructure that we would like to integrate with supports. So compute adapters, as the name suggests, are used to integrate with existing computational infrastructure. So it's used to execute like jobs and pipelines from within DeepForge. Each job actually will leverage the existing storage adapters to fetch and store data. So the data never goes through or is seen by DeepForge at all. The only thing DeepForge knows about it is the metadata that I showed before from the like artifact index, where I clicked on that little question, that little information icon when I was looking at the artifacts. Now, at the currently we only have 3 compute adapters that are supported: SciServer Compute, WebGME Executor Framework, which lets you again connect your own machine, and then server execution, which is of course disabled on the public deployment because that would have pretty serious scalability issues. Now I showed a little screenshot of the little compute subsection when you're executing a pipeline. Here. The other method of integration to existing infrastructure is through storage adapters. So these basically just need to be able to fetch and store data, as well as get a little bit of metadata about it, like size and such. Because DeepForge itself doesn't store any associated data. So like training data or trained models, even if you upload it to DeepForge, your browser will actually directly store it with whatever storage backend that you want to use. And it won't at any point be passing through DeepForge or the DeepForge server itself. Now, currently we support SciServer files and S3 object storage. There is a third option where the server basically just stores it as well. It's really useful or convenient when you're running it locally, but certainly this also would have scalability challenges on the public deployment. And we didn't really want to get into the space of trying to maintain a lot of infrastructure because a lot of natural sciences already have their own infrastructure, so it doesn't really make sense to introduce a competitor when it would be a lot more work, and there's not really a strong compelling reason for it. Okay, so these are the I wanted to mention these integration options, partially because if there are other sorts of integration or infrastructure, if people are using different types of infrastructure, I would certainly be quite interested in knowing which ones of these or what would be the most fruitful adapters to be added, especially if you're interested in using DeepForge. Not to make it like a sales pitch, but my point is that if with any interest in using it, I think it would be great to hear feedback about what people like and don't like, or would need or don't need, all of those important sources of feedback. Now, I showed one of the demos before with this redshift estimation task. Now there are other interesting. Let's see. So there are a couple other things I want to talk about. One of them is I'm going to answer Joseph's question here when he was talking about dependency management, and then time permitting, I'll get into a couple other really kind of exciting new areas or exciting upcoming things with DeepForge. So with Joseph's question about dependency management, in DeepForge. One second here. You'll notice that when we went over and we were looking at the resources tab, this isn't called architectures. I mentioned when I first introduced it, it's called resources, not architectures. Now, the reason why is because DeepForge, as mentioned early in the slides, there are these kind of two separate types of concepts that we talked about, the concepts related to pipelines and executions, and the concepts related to neural network architectures. Now, in DeepForge, there are technically these public deployments actually have DeepForge with an extension loaded. Now, the extension actually is what provides the deep learning capabilities. So the idea is that if you think about DeepForge more generally, we have these pipelines, and then you have things that people might want to create with visual editors, again, like these neural network architectures that people might want to use within their pipeline. So this could certainly be extended in a lot of different ways with modeling tools for various physics or astronomical concepts. But as a result, this is certainly related to dependency management as well. So in DeepForge, so you have the concept of DeepForge as well as DeepForge extensions, which you can think of as tooling within DeepForge to bring domain specific concepts into it, one of which being the concept of neural network architectures from the machine learning domain. So when you pull these other concepts in, these certainly might have their own dependencies, and this has to be included in your worker environment as well. So really, when you think about dependency management within DeepForge, currently there's the server will have its own dependencies, like a Conda environment. The worker will have its own Conda environment. But then if you load any extensions, these certainly might be adding dependencies to each of these environments. And then you have these operational level dependencies. So you have this kind of three-tiered, layered dependencies. Now that was maybe getting into the weeds a little bit, but I still wanted to kind of mention it at least in passing. And I'm hoping that answered Joseph's question. Great. All right. So now that the other topics or other two things that I wanted to point out in our little bit of time we have remaining is actually related to some upcoming concepts that we have around. Let's see, do I have around interactivity and data provenance. So I haven't really shown anything yet about data provenance. Basically, one of the directions directions that I'm excited about within DeepForge is that these pipelines are useful to build these reusable operations and components that we can leverage in different ways across different pipelines. And you don't need to write any code to operate at that higher level of abstraction. So it's nice in terms of being able to create these reusable building blocks that people can compose and execute as pipelines. However, it is sometimes nice to be able to, or one of the criticisms could be that, or one of the downsides, I guess, is that you need to create the whole pipeline before you run it. Now, this is not a problem at all if you have a decent idea of what you're doing and are trying out swapping out architectures or swapping out other hyperparameters where the pipeline is largely unchanging. But it can be useful sometimes to be able to get interactive feedback. And this is, again, an upcoming thing that's not available on editor.deepforge.org. I had to hop over to dev. Dev is tracking the master branch. So if you are going to use it, just realize that those things may not be as stable as the latest release. But anyway, so in this case, we're introducing some concepts like these interactive editors. Now, interactive editor basically lets you connect to a compute instance and maintain like this live channel, I guess, where you can get feedback right away. So even when I'm using SciServer, which has which supports batch compute, this is actually creating a job on SciServer's using SciServer's compute API, which is establishing a live connection to my browser. And then I can basically train my own neural network architectures in the browser and get feedback right here and play around interactively without having to compose a whole pipeline first. So as you noticed when I was running those pipelines before, sometimes they'll be queued for a moment and things like that. I don't know why this one is still connecting. Yep, so it is preparing to submit. It's queued. Okay. So again, there's only so much you can do about the existing infrastructure because some are optimized for batch and things like that. But in this case, we're kind of once we've acquired the instance, we can play with it for a bit and get feedback right away. So we can see it's submitted, but it's not yet started. Hopping back to the, again, SciServer jobs dashboard. So as soon as this does start, you'll see that on the left, we have parameters. This is we're basically working with a UI that's tailored specifically to for training neural network architectures. So we can specify the training data, so list of artifacts that we have, the architecture we want to use, and then just specify the various parameters here. I am going to just double check quick that this architecture is a meaningful one. Yeah, so this is a really simple architecture, just called architecture. It's just a small multi-layer perceptron. We have this small dataset. We can specify, let's see, I have 32 outputs. So I think this is being treated as a classification problem. So I'll just pick one of these. And then we could pick our optimizer. And if we have any questions about any of these, we can click on the info option. And this will hop over to the Keras documentation, which is for some reason running a little bit slowly to load right now. But then we'd be able to, try this. There we go. Now it finally pulled up. So we could, so this will tell you about like documentation about the optimizer, such like that. And similarly, if you click on the info button around the bosses, you can get that as well. So here, we can train it, and since my data is stored on SciServer files, we would need to authenticate with that. And then we'd be able to run it here and see that it's fetching the data, generating the code, and actually training the model. So this is one of the yeah, so we can see if this thing's still running. Now, since this is this is an unstable, not yet released feature, but it's an upcoming feature. It's a little bit dangerous to show in tutorials and demos, but I wanted to show one of the ideas that things have been going, and one of the last things was that we also there's also this concept of like exploring data provenance a little bit more. If I hop back over to the CIFAR 10 example that I was just working on dev. See, again, dev is very new. So if we did something here like, let's train this for very few epochs. So if you did something here where you're training like some new data, let's use the multi-layer perceptron. There is one of the latest things that we've been exploring as well is this idea of taking the history of an artifact. So basically, if we looked at like model here, and we created a pipeline based off of how or that would reconstruct it. So reconstructing your workflow to create the given artifact. Anyway, it's an upcoming thing, kind of a little bit of a it's an upcoming area that I'm pretty excited about, but it's again still very new and not yet stable. Do people have any questions? I realize I'm about at time. So
yeah, it's at the end of the 2 hours. So I ask people, if you want to ask questions, please raise your virtual hand. We can unmute you and you can talk directly. No? Okay. Well, I am very impressed by Brian's tutorial. It's very deep. For me, I don't know much about deep learning yet, but lots of new concepts really stoked my interest now. I'm going to look into DeepForge and gather all the links. A question for you, Brian. If people already have the account and they didn't get to follow on, can they contact you if they want to
of course
watch the video and ask questions?
Yeah, of course. If people have any questions, you can always email me, or you can hop on the Slack channel. I'm always happy to either set you up with an account. So it's still been kind of like we haven't opened up registration publicly, but anyone, of course, that's on here, and if they have any questions, can always reach out, and I'll hook them up with an account if they don't already have one, and I'm happy to help any way I can.
That's great. We have this recording, so people who didn't get to follow today can try to follow the recording and do it on their own. So thank you so much. And I want to thank the attendees also for your patience and enthusiastic questions and try to follow along. And it's really impressive. At the height, I can see only here on the Zoom, we had more than 50 people, but I don't know how many on the YouTube. Francesco?
On YouTube, I counted between 25 and 30. So that's a good number,
Yeah, there's a lot of passion and interest in the deep learning area. So thank you so much. And our first session for the general conference will start at 5:55 UTC time. You know, people all have different times. So hopefully to see all of you there. Thank you very much, Brian.
Yeah, thank you.